Hello, this is the video abstract for the paper, The Unruh Effect in Slow Motion, published in the journal Symmetry. First, let me tell you a bit about one of the most bizarre and untested predictions made by our current best physical theories, the Unruh Effect. Then, let me tell you about an experimental proposal that we put forward in this paper to potentially measure this strange effect for the first time ever. Imagine that you are hurtling through the vacuum of deep space at near the speed of light. In the distance, you see a thermometer fixed in the vacuum of space. You decide to decelerate. You slow to a momentary standstill, close enough to get a reading, before you reverse direction, accelerating now in the direction from whence you came. Afterwards, you notice something strange. The reading on the thermometer said absolute zero, just as one would expect in the coldness of space. However, seemingly in contradiction to this, the thermometer on your spacesuit registered some heat, despite the complete emptiness around you. Indeed, you're sure that you felt some warmth. How could this be? Is your thermometer wrong, or is it just a matter of perspective? In life, some things are a matter of perspective. The man on the left here sees a 6, and the man on the right sees a 9. At least in cases like this one, this is okay. We just understand that the two men are seeing the same situation from two different perspectives. Luckily, some things are not a matter of perspective. Both men here see a 0. And in fact, anyone approaching this situation from any direction would see a 0 as well. But what about the concept of emptiness? Both of these men here gesture at empty space. Are their claims about the space observer independent? That is there an observer independent notion of emptiness, or a vacuum, or a particle number? Both men here are in effect saying that there are 0 particles. Surprisingly, according to one of our best physical theories, quantum field theory, there's not an observer independent notion about emptiness or the vacuum. In particular, quantum field theory predicts the Unruh effect. What feels to one observer like empty space, this man here on the left, will feel to an accelerated observer, this man on the right, to be a bath of thermal particles. In fact, he'll see many particles, and they'll have some temperature. In particular, the Unruh effect says that the accelerated observer should feel a temperature which is proportional to their acceleration. And here is the equation for this. The temperature is some constant times the acceleration. Unfortunately, the Unruh effect is very hard to detect, and in fact, it's never been experimentally confirmed. This is because a temperature of just 1 Kelvin requires a huge acceleration of 3 times 10 to the 19 Gs, where G is the strength of gravity at Earth's surface. For context, astronauts faint at around 10 Gs. So this is a very, very high acceleration. And consequently, this means that any experiment which we set up in this way, as demonstrated in these pictures, requires astronomical distances and times. Whichever probe or observer or thermometer we use to measure this effect, it will take it some time to thermalize with the field. And now within that time, these high accelerations mean that we will travel tremendous distances and timescales. What we do in this paper is we propose a new experimental testbed for detecting the Unruh effect with relatively low probe speeds and accelerations, potentially orders of magnitudes below previous proposals. This solves the astronomical distances and timescales issue. And here on the right is a schematic drawing of our experimental proposal. We have a probe system entering a series of cavities or mirror boxes, each of them empty with a quantum field in its ground state. We consider the probe to accelerate through the first cavity and then decelerate through the second, and accelerate through the third and decelerate through the fourth, and so on. This is so the probe does not end up building up much speed. Any speed gained in one cavity is lost in the next cavity. And we go through these cavities quite quickly, so no real speed is gained in total. The main focus of our paper is to simulate this sort of scenario using novel computational techniques discussed in the paper. We show under what circumstances this probe thermalizes to a temperature proportional to its acceleration. That's the hallmark of the Unruh effect. We find that the probe does indeed thermalize to a temperature proportional to its acceleration in some regimes, and in other regimes it does not. We provide a full analysis of when this does and does not happen in the paper. Roughly, we find the Unruh effect exactly when the probe exits each cavity before it has time to notice that it is, in fact, in a cavity and not in empty space. If you're interested, please check it out. And thank you for your attention.